Welcome to the 8th lecture of my series on advanced mathematical physics. We are currently discussing differential geometry, and today's lecture will be on one particular topic and one topic only. It will be aimed at filling a gap that we had left out in our discussion on tangent vectors. Let me quickly remind you about tangent vectors in the first place. A tangent vector, Vp, at a particular point P in a manifold, is actually a map from C infinity M, the set of all smooth functions on the manifold M, to R, the set of real numbers. And this map obeys two basic properties. Firstly, it's a linear map, so acting on AF plus BG, where f and g are smooth functions and a and b are real numbers, it yields a times vpf plus b times vpg. So, the fact that vp maps functions to numbers tells you that it's a functional, and this particular property tells you that it's actually a linear functional. In addition to that, a tangent vector also has to obey a very, very important property, which essentially tells you that it's tied to a particular point P of the manifold. Acting on a product fg of two functions, what it yields is f of p times vpg plus g of p times vpf. Note that the coefficients of vpg and vpf in this case are the values respectively of the functions f and g at the point p. And this tells you that if you were to try to add two tangent vectors at two different points, you will not get a legitimate tangent vector. However, we did show that all the tangent vectors at a particular point P does form a vector space. You can multiply them by scalars and add them using obvious definitions. Like the product A times Vp of a scalar A, a real number A, and a tangent vector Vp is simply a functional which maps f into the number A times the number Vp of f. Similarly, Vp plus Wp, the sum of two tangent vectors at the point P, is simply defined to be something which, acting on a function f, actually gives us Vpf plus Wpf. And it should be pretty easy to show that with these definitions, all the basic properties of a linear vector space is obeyed. And this linear vector space is a so-called tangent plane to the manifold M at the point P, Tp of M. Now, a special set of vectors arise when we use a chart on the manifold. If you are given a chart u, phi, where u of course is a subset of the manifold M and phi is a map from that u to Rn, we end up with n coordinate functions, and that leads to the notion of coordinate curves. Curves on the manifold which you get when only one of the coordinates change and all the others don't. The tangent vectors to these coordinate curves passing through the point P provide us with a set of basis vectors to TPM. These tangent vectors are denoted by del xi p, and the way they act on a function f is as follows. The function f of course is defined on the manifold, but using it we can define the proxy function f composite phi inverse, which actually acts on phi u, a bunch of n real numbers. Now if you were to take the ith partial derivative, capital Di, of this function f composite phi inverse, and evaluate that at the point phi of p, the point on phi of u, which gives you the coordinates of the point p according to your chart, then you get a number which is defined to be del xi p acting on f. Now the notation del xi p is meant to remind you of this being a partial derivative. It's just that the partial derivative is calculated not really directly on the function f, but on the composite function f composite phi inverse, which is a proxy function whose argument really is a bunch of n real numbers and the resulting thing is a real number. Here you can do ordinary partial derivatives, and that's what the capital Di on the right hand side denotes. So the del xi in the notation is meant to convey the basic idea that there is a partial derivative that is really being done. And as I have said before, the fact that you are actually differentiating f composite phi inverse should not come too much as a surprise, or should not even look too unfamiliar. Whenever you talk of a function on a manifold, usually it is the composite function you're talking about. When you're talking of a function defined on, say, the surface of a sphere, you typically talk of a function of theta and phi. That really is not the function f, is the function f composite phi inverse, which given the arguments phi of p, the values of theta and angle phi, returns you the numerical value of the point p of f, which returns to you the numerical value of the function f at the point p whose coordinates are these angles theta and phi. Of course, you must have realized that when I started talking about this particular example, I faced a problem that I was using the letter phi for two different things. One, for the map which maps the point P onto the coordinates, and the other as a name of the angle which is one of the coordinates used in the spherical polar coordinate system. I hope this dichotomy will not be too confusing to you at this stage. Now, you must have noticed that I have underlined the word basis above in red, and there is a very good reason for that. The important point is we have not yet proven that del xi p's actually form a basis. We have claimed that, and we have actually went ahead and talked about certain properties which follow from that, but the proof of this has not really been given. What we had proven in the last lecture was that the del xi p's are actually linearly independent. So, one part of the proof that they form a basis is already given. But what we do have to prove to confirm that this is a basis is that these vectors actually form a spanning set of TPM. In other words, the claim that we are making here is every vector VP of TPM can be written down as a linear combination of the del xi p's, where I of course runs over all the possible coordinates 1, 2 up to n. Indeed, a further part of the claim is not only is VP a linear combination of del xi p's, we know precisely what that linear combination is. It's actually VP acting on the ith coordinate function, that of course yields a number, times del xi p. Of course, the sum over I here is assumed. We are using the summation convention throughout, unless of course otherwise mentioned. We had actually talked about this particular formula for VP in the last class, and we had actually made use of it to show several things, including the fact that when you change your coordinate system, or when you are in an overlap region of the domains of two charts, the components of a tangent vector change in the standard way which phases are familiar with. And indeed, we had also shown in the last lecture that if you grant me the fact that every VP can be written down as a linear combination of the del xi p's, then it has to be this particular linear combination, VP acting on xi, del xi p. However, we have not really shown this basic result. As yet, the fact that every vector can be written down as a combination of the del xi p's is basically the one thing that I want to demonstrate in today's lecture. The reason why I had not talked about that in the last lecture and had deferred it to a separate one is simply the fact that the proof of this result is not as straightforward as the rest of the things that we had discussed there. It takes a bit of background mathematics to be able to comprehend the proof. So first we are going to talk about the basic background needed, which is a standard result from real analysis. The proof of the claim requires the mean value theorem. Now, the mean value theorem should be pretty familiar to anybody who has done a course on real analysis, but the particular form in which we need this may not be familiar to somebody who has not done a course on multivariable real analysis. So let me just give you a brief reminder here. First, the standard mean value theorem for functions of a single variable. If you have a single variable function, f, a C1 function, a function which is differentiable once continuously from an interval a to b to r, then there exists a point C in the open interval between a and b where the following holds. F prime C is equal to the difference of the values of f at the two endpoints divided by the interval size, fb minus fa by b minus a. Now let me try to show you what this means in a picture, and it should be pretty clear to you that this is something which has to be true. The formal proof of this can be found in any calculus text, and I am just omitting that for the time being. But what this means geometrically is the following. Suppose I have this C1 function f whose graph I have drawn here. So this is f of x drawn along the y-axis. This here is a point A and this is the point B. And I know that the function f is defined at least in the closed interval between a and b. So f of a and f of b are also defined. Now this quantity fb minus fa by b minus a is nothing but the slope of this line which joins the 2 points a comma fa on this side and b comma fb on this side. So it's basically a line joining 2 points on the graph. A chord of the graph. What the theorem actually tells you is that there is a point C somewhere in between A and B where the derivative of f at the point C, which means the slope of the tangent to the curve at the point C, must be equal to the slope of this chord. So somewhere along this curve there is a point where the tangent is parallel to this chord. That's all that this theorem means geometrically. Of course, you can rewrite this in another way. F of b has to be equal to f of a plus f prime c into b minus a for some point c in the open interval between a and b. Such a point c always exists. That's what the mean value theorem for one variable is telling us. Let us now go on to talk about the version of mean value theorem that we will really need, a version which involves multiple variables. So for this, we are talking about an open set in Rn. This is not a general manifold at this stage, this is just Rn. So U here is an open set. And the function h that we are going to talk about is a function which maps this U onto R. So given n real numbers within this set U, you end up with a single real number as a result of the application of H. And what we are claiming is this H is C1. Let me remind you that what this means is that all the partial derivatives of the function capital H with respect to its n arguments exist and are continuous. Now let us consider A and B as 2 points in this n-dimensional set U with one very important property. We are defining LAB as a set of points 1 minus t into A plus t into B, where t is a real number between 0 and 1, both endpoints inclusive. It's pretty easy to see what this means geometrically. If you were in R2, then what you are saying is, if this point is A and this is B on the plane, the point 1 minus t into A plus t into B is simply a point somewhere in between. In fact, when t is equal to 0, then this point is exactly A, and when t is 1, it's B. So, this set of points as t changes traces out this straight line in R2 in our example, but it should be obvious that in Rn, this should be a straight line joining the 2 points A and B. That's why we have written this as L, A, comma B, L for the line. The idea is that we are demanding that A and B are 2 points in U, such that the line joining A and B are also in U. So our set U contains every point in this line. This will work, for example, if this is your U. This will work if this is A and this is B, because the line joining A and B is in U. But it will not work, for example, if this were A and this were B, because the line joining A and B then will have a part which sticks out of U. We are assuming that A and B is such that the entire straight line joining A and B is contained in my domain U of the function H. Now if that happens, then what we can do is make use of the mean value theorem for single variable functions by introducing a single variable function from R to R, this small h, which you define in this particular manner. You take h of t as capital H acting on 1 minus ta plus tb. Note that as t goes from 0 to 1, this point 1 minus ta plus tb is somewhere on LAB, or somewhere in this set, and this set is inside the domain U, so capital H can of course act on it. So h of t becomes a function which actually is not really R to R, is really defined from 0, 1 to R. Now if t goes beyond 1, then you are actually moving beyond B along the straight line, or if it's negative, then you are actually on the other side, beyond A, and that might very well be outside my domain. So I'm not going to make any statement about h being a function from all of R to R, but h definitely is a well-defined function from 0 to 1 to R. Now, this small h has certain obvious properties. Small h at 0, when you put t equal to 0 here, is nothing but capital H at the point A. And when you try to calculate small h at 1, you end up with capital H of B. So, small h at least has capital H values at A and B as two endpoint values. So, we have small h at 0 and small h at 1. What we know from the mean value theorem is this ratio must be equal to the derivative h prime at some t0, where t0 is a value between 0 and 1. So what we need to do is take a look at what h prime t is. Now, h prime t, of course, is the rate at which h changes with t. But this is how small h of t is defined. So it changes with t because of two things. It changes of t because 1 minus t into a depends on. It also changes because tb changes with t. And it's pretty easy to see that this, if you rewrite this in the form h of a plus t into b minus a, h prime of t simply becomes bi minus ai times the ith partial derivative of capital H, summed over I of course, evaluated at the point 1 minus t into a plus t into b. That is, evaluated wherever this point in the line joining a and b is. So, mean value theorem, as we said, tells you that there must exist a t0 between, actually a t0 in the open interval 0 to 1, such that h1 minus h0 is equal to h prime t0, or h1 is h0 plus h prime t0. And going back to the fact that small h1 and small h0 are actually capital HB and capital HA, what we find is capital H of B must be equal to capital H at A plus bi minus ai into dih evaluated at 1 minus t0 into A plus t0 into B. With this result from real analysis under our belt, we will now proceed to prove that the del xi's actually form a spanning set for TPM. The way in which we do that starts by examining that notion of the proxy function given a particular chart u, phi. Now if u, phi is a chart on the manifold M, denoted by this orange boundary here, and u is this magenta boundary enclosed sets, then phi of u happens to be some open subset of Rn. I've shown n equal to 3 simply because that's something can still show on two-dimensional paper. At least a projection of that can still be shown. You should have to imagine that this is actually Rn for some positive integer n. And P maps onto a particular point phi of P. The idea behind the proxy function, let me remind you, is the following. If f is a function on the manifold, a smooth function which maps points on the manifold to R, this capital F function is obtained by composing F composite phi inverse. That is, you apply the phi inverse first to take a point in phi of u into u and then apply F on that. In this way, F composite phi inverse maps phi of u, an open subset of Rn, onto R, and this is where we can do ordinary calculus. And this is why when we want to talk about F as being a C infinity function on M, what we really do is construct F composite phi inverse using the chart u, phi, and then look at the composite function capital F. If that happens to be C infinity in the standard sense of calculus, then small f is actually C infinity n. Here we already know that f is C infinity n. From that we are arguing that capital F, F composite phi inverse, must be a C infinity function on a subset of Rn to R, and hence being C infinity is definitely C1, so it satisfies one of the basic conditions that we have before we can use the mean value theorem. The next part may look a bit complicated, but all we are really doing is ensuring that the points P and another point Q that we use in our discussion satisfies the conditions for the mean value theorem as well. It's really not the point P and the point Q that we are after. After all, they are points on the manifold. We can't really directly use mean value theorem there. We can use mean value theorem directly on phi of u. So what we are really looking at are points phi P and phi Q. Phi P, of course, is a fixed point as long as P is fixed. I have to choose Q in such a way that phi of Q along with phi of P satisfies the basic conditions for the application of the mean value theorem, which remember is not only that phi Q and phi P is in the domain, in this case phi of u, of our function capital F. The straight line joining phi P and phi Q must also lie entirely inside the domain. Now, for this what we will do is the following. Here we are seeing this in a bit more enlarged fashion. Say point P maps onto phi of P. Now phi of P is an interior point of phi of u. It has to be because phi of u is an open set and therefore all points are interior points. And therefore, there must exist some positive value of R such that the ball B phi P R, that is a ball centered at phi P of radius R, must be completely contained inside phi of u. So I am showing the ball here by this blue outline. This is B phi P R. Now in order to ensure that my point phi Q satisfies the condition for the mean value theorem, what we will do is take a phi Q which lies inside the ball. In other words, I will take Q to be somewhere inside phi inverse of B phi P R. So if we apply phi inverse on this blue set, that is the set bounded by the blue line in this figure, maybe I will get something looking like this, something bounded by the green line here. That's my phi inverse B phi PR. I've chosen Q somewhere inside that. As a result, phi Q will end up being somewhere inside this ball. And therefore, it's easy to see that both phi P and phi Q and the entire line joining phi P and phi Q are actually inside the ball. That's a standard geometric property of any ball. And because the ball is contained entirely inside phi of u, the line joining phi P and phi Q, as well as the points phi P and phi Q, must be contained inside our domain phi of u of the proxy function. So we have all the conditions ready for applying mean value theorem. Now that we have the conditions ready, let us consider this particular C infinity function, the one which we have been considering so far, capital F, F composite phi inverse, which is a map from phi u to R. According to the mean value theorem, there must be some point t0 between 0 and 1, some value of t0 between 0 and 1, such that f of q minus f of p, which is actually capital F of phi of q minus capital F of phi of p, in other words, capital F of x1q, x2q up to xnq. Remember, phi of q is just a bunch of n numbers, the n coordinates for the point q, minus capital F of x1p, x2p up to xnp. This must be equal to xiq minus xip, the change in the x coordinates between q and p, times the partial derivative dif, of course summed over all I, evaluated at the point t0 or at the point given by the number t0 on the straight line joining phi p to phi q, the point 1 minus t0 phi p plus t0 phi q. Here, note that this is just a restatement of f of b minus f of a equals bi minus ai times dif evaluated at 1 minus ta plus t0a plus t0b. Now, if we hold the point P fixed, then what will this number dif evaluated at 1 minus t0 phi p plus t0 phi q depend on? The only thing that you really have free here is your choice of the point q. Once you choose q, phi q automatically gets chosen, and then the value of t0 gets chosen along with that. Of course, the particular functional dependence of t0 on q may be very complicated, but it is at least a given fact that once you choose phi of q, you are going to get a t0 value, and this whole thing is going to come out from that. So ultimately, this thing is some function of q. In fact, for the ith partial derivative, this is going to be the ith function giq. So I'm defining this to be giq. And as a result, what we have in addition is the following. If you were to evaluate gi, this function at point p, you are sure of what value you are going to get. Because when p and q coincide, then t0 has to be 1. In fact, then whatever value t0 takes, this point is nothing but phi of p. So gi at point p is dif evaluated phi p. That's of course the ith partial derivative of small f composite phi inverse evaluated at phi p, which is nothing but del xip acting on f by definition. So I may not know the function giq. All I know that the function giq exists. It may be a very complicated function. However, what we know for sure is that its value at the point p is nothing but the ith partial derivative of the proxy function capital F evaluated at phi p, or the result of the ith coordinate vector acting on the function f. So what we have written here can simply be written down as f at q is f at p plus xiq minus xip at p times giq. Or in other words, in terms of these functions gi, because there are n of them, f the function, note that this is true for all points q inside that domain, so at least locally, f that function is given by f of p plus xi minus xi's value at p into gi. This is the same statement as this. I've just the function itself, and here I'm talking about the value of the function at a particular point q. So this is your function f. This actually is all you really need to complete the proof. So now the question that we are going to address is, if Vp is some tangent vector at the point P, what happens when we apply Vp on f? Remember, f is any arbitrary smooth function so far. So Vp acting on f, using the linearity of tangent vectors, is going to give me Vp acting on Fp plus Vp acting on this product. Now Vp acting on Fp is pretty straightforward. We had already proven in the last lecture that Vp acting on a constant, and that's what f of p is. The value of the function f at a point p, so it's basically a constant function. Vp acting on a constant function is 0. So that is out of the way. What about this? This is the product of two functions on which Vp acts. So we will get to use a derivative property. It's going to be Vp acting on xi minus xip times the value of gi at p plus xi minus xip evaluated at p times Vp acting on gi. Now this might seem to be a bit of a dampener because, as we have said, gi is a pretty complicated function which will depend on the details of the function f, and so Vp acting on gi may be very difficult to figure out. However, note that this actually multiplies the value of the factor xi minus xip, value of this function at the point p, which thankfully happens to be xi of p minus xi of p, and that is 0. So this term, the term which could have given us a lot of trouble, drops off. On the other hand, Vp acting on xi minus xip is simply Vp acting on xi. Xip once again being the constant numerical value or a constant function. Vp acting on xip will be 0. So this will just give me Vp acting on xi times gip. But note that we have said that gi may be a very complicated function, but its value at the point P is well known. Its value at the point P is nothing but del xip acting on f. So what we have is the following. The tangent vector Vp acting on f, any tangent vector, is basically given by this expression, Vp acting on xi. These are of course numbers which you get when the tangent vector acts on the I coordinate functions, times the coordinate basis vectors del xip. Of course, we are now really in a position to call them basis vectors, because what we see is that because it is true for all f, every tangent vector Vp is given by Vp xi del xip. In other words, you have the del xips, you can linearly combine them to form any tangent vector Vp you want. So every tangent vector which is at the point P can be written down as a linear combination of del xips. So the del xips form a spanning set. We had already proven in the last class that they are independent, and therefore del xips form a basis. An immediate corollary of this was the very important result that we talked about before. Since del xips are n in number, one for each coordinate, it follows that the tangent plane at the point M has one basis at least, which is made out of these coordinate vectors, and that basis has n elements. So TPM has to be n-dimensional. It is an n-dimensional linear vector space if a manifold happens to be n-dimensional. So if a manifold locally looks like Rn, its tangent plane basically is Rn. With this proof, we have closed a very important gap in our study of tangent vectors and tangent planes. In the next lecture, we are going to explore more properties of vectors and also talk about how you can push vectors from one manifold to another. But for that, we will have to wait for the next lecture. Bye for now.